We're going to use a technique here with the probability tree. The probability tree looks like this, and it's useful, especially when you have probabilities that are not equal. So, for example, a lot of the things we've been doing up until now, each of the events has an equal chance of happening compared to the other events. And when you have a probability tree, you can use different probabilities that aren't one half and one half. Okay? So, like in this example, you see um, we're doing the chance that you roll a 6 and the chance that you don't roll a 6. And the chance that you roll a 6 is 1/6, and the chance that you don't roll a 6 is 5/6. So then you can see that, like, going down this leg of the tree, you have, or this branch of the tree, you have a 1/6 chance, and this one is a much higher chance, 5/6. Okay? And then if you roll twice, then what happens is, like, each layer of the tree you have you break it into two paths from each separation point. I'm sure you've done these before, but let's review them. Okay, so if you have a bag that contains 6 red and 5 blue counters, you're going to choose one at random and then you put them back in the bag. Then you choose again. So you can see that, like, on the first drawing, uh, you're going to choose either red or blue. There's a higher chance that you're going to get red than blue, right? Because there's 6 red and there's 5 blue. What's the chance that you're going to get red? The chance you're going to get red is 6/11. The chance that you're going to get blue is 5/11. At the second time you draw, they put the red or blue that they drew out the first time back in the bag. So again, you have the same thing happen. You have 6/11 or 5/11. 6/11, 5/11. Okay? All right, so that's what it looks like. Find the probability that exactly one red counter is chosen. Okay, so let's see. Which of these events is one red counter chosen? Uh, let's see. It would be like choosing a red counter and then choosing a blue counter. It would be choosing a blue counter and then choosing a red counter. But the other paths are either choosing 2 red or 2 blue, so they don't count. Now let's figure out the probability of choosing one red counter. So that would be 6 divided by 11 times 5 divided by 11. And this one would be 5 divided by 11 times 6 divided by 11. And so we just add those together. So for A, we're going to have 30 divided by 121 plus 30 divided by 121, we get 60/121. Okay? And then what about for B? Find the probability that at least one blue counter is chosen. Okay, in this case, let's see. One blue counter, at least one blue counter. So this would be okay, this would be okay, and this would be okay. The only one that's not okay is the one at the top. Okay, so there's a couple ways you could do this. You could figure out the probability of each one of these 3 legs, or you could probably find the probability of the one leg that doesn't satisfy it and then subtract that from 1. But we'll do this way. 5/11 times 5/11. So we have 30/121 plus 30/121 plus, and this last one is 5/11 times 5/11, which is 25/121. So that's equal to 85/121. Okay. C. Find the probability that one of each color is chosen. So that would be red blue and red blue. One of each color was chosen. That would be the same thing as probability of A. So I could just put the same answer as A, 60/121. Because if exactly one red is chosen, that means exactly one red is chosen, and exactly one blue is chosen. So that means one of each color was chosen. So C is the same as A. D. If one of each color was chosen, what is the probability that blue was chosen on the second pick? Okay, so to figure that out, so we say the probability of blue on the second pick is equal to the probability that blue was chosen on the second intersect with that red and blue were both chosen. And then in the denominator, we're going to put the probability that red and blue were chosen. So the probability that red and blue were both chosen, that we know is 60 divided by 121. The probability that blue was chosen second and red and blue were chosen would be this leg here. So that would be 30 over 121. So the chance that that would happen is actually 1/2, right? E. If at least one blue was chosen, what is the probability that blue was chosen on the first pick? Well, we know that the probability that at least one blue was chosen is B, so we'll put that in the denominator. 85 over 121. Now we find the probability of one blue chosen and that the blue was chosen on the first pick. So that would be this leg here. Okay, so that would be 5 over 11 times 6 over 11. At least one blue was chosen. Could be this one too. Okay, so it would be both of these. So it would be one blue was chosen. What's probably the blue was chosen on the first pick? At least one blue was chosen. So it could be this one too, right? So the probability at least one blue was chosen was all three. Now, how many of these was blue chosen on the first pick? This one and this one, which would be 55 over 121. Okay, so that would be 55 over 85, something like that. Okay, let's go to number 3. To get to work, I must go through 2 sets of traffic lights. At 6th Avenue and then at Dover Road. I got delayed at 6th Avenue with probably a 7/10 and at Dover Road with probably a 3/10. Okay, so draw a tree diagram to show that the possible delays on my way to work. So, first thing, I must go through 2 Okay, so I drew this tree diagram. The first branch is what happens at the 6th Avenue, whether you're on time or delayed. And then the second branch is what happens at Dover Road. So the first branch, I go 3/10 chance that it's on time, 7/10 chance that it's delayed. Dover Road is 2/5 chance on time, 3/5 chance delayed. So we draw that 2 times, once for each of the branches. Now it says find the probability I get delayed only once. So that would be, it would be one delay here or one delay here. So those are the 2 possibilities. That would be 3/10 times 3/5, and this would be 7/10 times 2/5. So that would be 9 over 50 plus 14 over 50. So that would be 23 over 50. Okay, that's A. B, find the probability I do not get delayed at all. So that would be do not get delayed at all. So that would be on time, on time. That would be this path. So that is a 3/10 times 2/5 chance, which would be equal to 6/50 for B. Okay, all the other possibilities you're delayed at least once. C, given that I get delayed exactly once, what is the probability it was at 6th Avenue? Okay, so I already know that I was delayed exactly once. So let's say that that is probability of A, so that's 23 out of 50. We're going to put that in the denominator. In the numerator, we're going to put the probability that I was delayed exactly once, and it was at 6th Avenue. So that would be this path, right? So what is the probability that I was on this path? It would be 7/10 times 2/5, which would be 14/50. So the probability here would be 14 over 23. D. Given that I get delayed, what is the probability that was at 6th Avenue? Okay, so that means, what is the probability that I'm delayed anywhere? And then the top is going to be, what is the probability I'm delayed at 6th? Okay, the probability that I'm delayed at 6th is 7/10, right? It would be anything here. Okay, either one of those. So I would put 7/10 as the probability that I was delayed at 6th. And then the probability that I'm delayed at all would be any of them except for the top one. So it would be this, this, and this. So it would actually be the inverse of the probability I do not get delayed at all, which we already know is 6 over 50. So it's the inverse of that would be 44 over 50. So 7/10 divided by 44 over 50 that's equal to 35 over 44. Okay. Number 5. The probability that it will rain today is 0.2. If it rains today, the probability that it will rain tomorrow is 0.15. If it is fine today, then the probability it will be fine tomorrow is 0.9. Well, this is kind of a complicated one. So the probabilities seem to change depending on the probability before. But that's the good thing about probability trees. Even if the probabilities change in certain cases, it really doesn't make the probability tree any more complicated. So this is the first day, and this is the second day. So the first day, what is the chance that it's going to rain, and what is the chance that it's not going to rain? Rain, not rain. Rain, not rain. When you put the line above the letter, that kind of means that it's not going to happen. So the probability that's going to rain today is 0.2. The probability that's not going to rain today is 0.8. The probability that it rains, if it rains today, the probability that it will rain tomorrow is 0.15. And otherwise it's going to be Let's go to 85. If it is fine today, then the probability it will be fine tomorrow is 0.9. Okay, so that's how it shapes up. Given the at least one day is, find the probability that at least one day will be fine. So that would be either this path or this path or this path. Okay, so everything except for raining both days. Well, raining both days, we find that it's 0.15 times 0.2. That's raining both days. So A would be 1 minus 0.15 times 0.2. Okay? I'll let you figure that out. B, given that at least one day is fine, what is the probability that it was today? Okay, so let's put, so the probability that one day is fine, and on top we're going to put probability that one day is fine and it was today. Today, fine. Okay, so what's the probability that that one day is fine? At least one day is fine. That would be the probability of A, which we'll put down here. Okay, and then in the numerator we'll put the probability that one day is fine and that day was today. So that would be it would be this. No, it would be this path, right? The probability that today was fine is 0.8, as you can see. Okay, so you can figure that out. Take the answer from A and you put it down here. C. Given that at least one day is fine, what is the probability that both are fine? So on the bottom, you're going to have the probability that one day is fine, at least one day is fine, which is probability of A. And on top, you're going to put the probability that both are fine. Both fine. The probability that both are fine is, we already found that. It's 0.1, it's 0.2 times 0.15. 0.12 times, I'm sorry, 0.2 times 0.15. And then in the denominator, you have probability of A, from A. Okay? That wasn't too bad, was it?